Hello students, this is lesson U4A03b. By the end of the lesson, you should be able to say, I can use properties of sides and diagonals to identify a rectangle on a coordinate plane. So as we've discussed in the previous lesson, these are the two properties that we use to show that a quadrilateral is in fact a rectangle. And we're going to try to apply these ideas to a coordinate grid, to a coordinate proof. So looking at this, okay, for the first property, where it says we need to show that a quadrilateral, we need to prove that a quadrilateral is a parallelogram, and then with at least one right angle. Now, in order for us to do this, okay, we can use a couple things. Well, actually, not a couple things. We use only one thing, and that is the slope formula. So how are we going to accomplish this using the slope formula? Well, we need to show that opposite sides are parallel, and after we've applied the slope formula 4 times, we need to articulate that adjacent sides have negative reciprocal slopes, because that is what's going to allow us to then declare that we have right angles. All right. Similarly, okay, if we can show that a quadrilateral is a parallelogram with diagonals congruent to one another, okay, we can show that a quadrilateral is in fact a rectangle. So how are we going to do this? We can use the distance formula to show that the diagonals are in fact congruent to one another by showing that they have the same length. So we use the distance formula to show that the diagonals are congruent. Now, whichever way you want to choose to show that the quadrilateral is a parallelogram, that's entirely up to you. You can use, again, the slope formula. You can use the distance formula to show that opposite sides have the same length. Whichever is to your liking. You can also show that the diagonals bisect one another, right? Remember that that was one of the properties of a parallelogram. If the diagonals bisected one another, then that would be sufficient information to show that the quadrilateral that you're dealing with is in fact a rectangle. So yes, distance formula to show the diagonals are congruent, but also, you know, one of those other properties to show that this is in fact a parallelogram. Okay, so let's take a look. First example, we need to show that GEOM is a rectangle, and I give you the coordinates for G, E, O, and M. If you have graph paper, if you have graph paper handy, this would be a good time to use it. So we're going to show that GEOM is in fact a rectangle, and we're going to approach this by showing that opposite sides are parallel and that there is at least one right angle. Pause the video for a moment to see if you can approach this on your own. And welcome back. So what we're going to do is we're going to find, to determine whether opposite sides are parallel or not, we are going to use the slope formula. We're going to find the slope of GE, EO, OM, and GM. So the slope of GE, we're going to do 5 minus 3 over 2 minus 1, which then just becomes 2. The slope of GE is 2. We're going to now approach it the same way to find the slope of EO, 3 minus 5 over 6 minus 2, which turns out to be negative half. The slope of OM is 2, and the slope of GM is negative 1/2. This is not enough information for us to just declare that this is a rectangle. We need to make a statement, okay? We need to show that this is in fact a rectangle by, again, declaring that since slopes of GE and OM are the same and the slopes of EO and GM are the same, then opposite sides are parallel. Since slopes of GE and EO have negative reciprocals, then GE and EO are going to be perpendicular. GEOM is a rectangle because opposite sides are parallel and there is at least one right angle. Just like with the coordinate proof when we were proving that a quadrilateral is in fact a parallelogram, we need to do something very similar here as well. A declaration at the end is absolutely necessary. We're going to approach the same problem again, but we are going to approach it a little differently. We're going to repeat the problem by showing that diagonals are congruent and that they share the same midpoint, as I've suggested in the beginning of this lesson here. You can, of course, show that this is a parallelogram not by finding that the diagonals share the same midpoint. You can, of course, always find that opposite sides are parallel, opposite sides are congruent, but we're going to approach it this way. Pause the video for a moment to see if you can do this on your own. And welcome back. So we're going to find out what the length of the diagonals are. So we're going to find the length of EM and then the length of GO. So the length of EM, as it turns out, will turn into a length of 5. The length of GO, as it turns out, is, again, a length of 5. Did you have to go through this extreme measure to find out what the length of the diagonals are? Of course not. You could have also just counted what the length of GO was by counting the number of boxes on the coordinate grid. For EM, however, it does require you to form that right triangle and to use a Pythagorean theorem, but regardless, you should be able to arrive at the same conclusion, whichever method you'd like, either counting or using Pythagorean theorem. We now need to find the midpoint of EM and the midpoint of GO. The midpoint of EM, if we find the averages of those two coordinates, as it turns out, it will be 7/2, 3. If we find the midpoint of GO, it too will be 7/2, 3. And that makes sense because the midpoint is in fact right there, and it is going to be 3.5, 3. So we do need to declare that this is in fact a rectangle, and the reason is, since diagonals are the same length and diagonals share the same midpoint, then GEOM is in fact a rectangle.